So hello, welcome to More Physics 2. Today we will continue the second half of the next to last chapter. As I said before, I do plan on doing a final exam review. When that's going to be is the poll thing is still open. I plan on closing that poll tonight, and so I'll send an email out on Thursday. Cat hell. I'll send an email out on Thursday saying what it's going to be. Where we were left off, though, was we were talking about the energy of photons and in general about the discovery of photons and the photoelectric effect. And so I'm going to pick up with talking about another thing that was discovered around the same time, an X-ray. X-rays, first discovered in 1895, so a little bit earlier, by a man named Wilhelm Röntgen, was so named because they had no idea what the hell they were. The X is just to be like a placeholder for an unknown. What people knew, though, is that if you take really fast moving electrons and you slow them very quickly, they produced something, some unknown type of ray. Generally, what it was you make electrons, how they were slowing them down quickly was they were having them fly into a wall. That they were accelerating electrons, shooting them at a wall, and then when they stopped quickly because they hit a wall, yeah, rays came off. This is one of the first X-ray devices shown here on the right that if I kind of turn sideways, you can see is the same as this theoretical version. That's just hooked up to a circuit, launching electrons and hitting metal. It's kind of interesting because we now know X-rays are part of electromagnetic radiation spectrum. It's very, very short wavelengths. And so it's kind of interesting because this is saying if you shoot electrons at a piece of metal, you can produce electromagnetic rays. And the photoelectric effect was if we shoot electromagnetic rays at a piece of metal, we can make electrons move. So hey, some nice parallel to that. Now, because of the short wavelength of X-rays, that's why they can penetrate most materials with ease, that they have a really long wavelength so they can pass through the crystalline lattice of solids. However, small wavelength means high frequency. High frequency means high energy. That's why it's not always a good thing to be bombarded by X-rays, is it has a large amount of energy. Now, if you look at the spectrum from a tube just like this and look at the rays that are emitted when you shoot these electrons at this piece of metal, you're going to get a diagram that looks like as follows. It has two major parts. The broad spectrum, which is just a big area that has a good amount of intensity wavelength, and the sharp peaks. These sharp peaks being certain wavelengths that they have much, much, much higher intensity at those exact wavelengths. Now, to see these sharp peaks, the electrons need to be accelerated past a certain speed. And if they're slow in that speed, they don't come up. And we just accelerate the electrons with voltages. We basically apply a lot of voltage to an electron, shoot it off, get it fast enough, those peaks show up. Whatever the voltage required to make those peaks show up is called the threshold voltage. Now, where these peaks occur, like for this one, they're about 60 and 73-ish picometers. That depends on what the material is you shoot the electrons at. And different materials will have different peaks at different spots. I don't know off the top of my head what type of material this is. I didn't write it down. But it's a way to identify what a material is. Now, the reason for this is kind of interesting. What happens is when you shoot the electrons at the piece of metal, you're shooting the electron at atoms because that's what everything is. As the electrons approach these atoms at high speed, what's going to happen is it's not just something hits a wall. The electrons are small enough that the electrons can penetrate into atoms. And so what's going to happen is they're going to penetrate till they get close to a nucleus, nucleus being the positively charged center of an atom. When these fast-moving electrons approach the nucleus, what's going to happen is there's a Coulomb force between the electron and the protons of the nucleus. And that is going to cause these incoming electrons to be deflected. And what happens is when they deflect, that means they turn. If things turn, that means they accelerate. And anytime you have acceleration, you have a change in kinetic energy. If you have a change in kinetic energy, that means a change in energy, and energy must be conserved. And so a photon is emitted to work out conservation of energy. That because we deflect these electrons, we reduce their energy, and the reduced energy is manifested in the form of a photon, with a photon of energy HF. Um, Now, if instead of the things being deflected, because this is what we're saying is the electrons are coming flying in and kind of going, meow, they're going off a different direction. If instead of deflecting the electrons, if you stopped them, they actually did hit a solid wall and stopped moving, what would mean is that the photon emitted would be the exact same amount of energy as the electron had. Because if you take all of the electron's energy and take it all away, then all of that energy goes to the photon. What that means is the energy of the electron, which would be its kinetic energy, but the kinetic energy of an electron is eV, that the kinetic energy of the electron, eV, would equal the energy of the photon, this being the maximum amount of energy the photon could have, which means it's the maximum frequency the photon could have. Keep in mind that frequency is equal to speed of light over lambda, so I could also relate this to the wavelength. You'll note though I said lambda min though. Once again, because the frequency goes up, wavelength goes small. And therefore there is a minimum wavelength that can possibly be produced. And that's why the broad spectrum has a kind of, the broad spectrum, you go on the high side, just kind of slowly comes down and, oops, I told you to write. It slowly goes down and it's going to approach zero but never fully hit it. On this side, for minimum wavelength, it goes and has a set zero. It's right there. That's the spot where there's nothing else. That's because that is the minimum wavelength required, because that's going to correspond to the maximum energy they could have if we stop the electrons as opposed to bending them. Any questions?
Nope.
Example problem. Minimum X-ray wavelength produced is 13.5 times 10 to the negative 12 meters. What potential are the electrons accelerated in order to generate this radiation? If you want to find what potential, there's the equation for minimum wavelength. I'll multiply both sides by V, divide both sides by lambda, and plug in. Now, if you look at this, 92,000 volts ended up being the answer. To make X-rays, you use a lot of voltage. It is a very, very high voltage power supply to do this. Now, this leads to something kind of neat and involving one of those people from that photo we looked at the beginning of this chapter on Monday. You see, once people started to understand this is where the X-rays came from, people were like, okay, X-rays is not just a ray like people thought. It's an electromagnetic ray. It's a light wave, which means it's not only a photon, but it's also a wave. That yes, we're releasing a photon of this energy, but that is a wave. And if it's a wave, it has to be able to go under have diffraction, like any other wave. The single slit and double slit refraction we did 2 chapters ago, X-rays have to be able to do it too. But the thing is, we said diffraction only happens if the slit is thinner than the wavelength. And the wavelength of X-rays is really goddamn small. So to see diffraction from an X-ray, you need a slit smaller than 1/10 of a nanometer. And a guy, who I'll go to who he is in a second, said, yeah, we can do that. You want to know how? Sign it at salt. You see, salt is sodium chloride. And sodium chloride has a nice crystalline lattice. And the sodium and chlorine atoms, ooh, that bothers me. That L should not be capital. the sodium and chlorine atoms make a grid, and there's some space between them. And what they basically realize is a crystalline piece of sodium chloride, aka table salt, could act like a series of slits and could act like a diffraction grating. It doesn't have to be salt, it could be any crystalline lattice, but we're going to deal with salt for now. Now, salt has a nice square grid. And because it has a square grid, the diffraction would depend on the angle the light hits. And you can have constructive interference or destructive interference. And we can look at the interference pattern. This is called Bragg's law. And it was created by William Bragg, one of the people in the photo at the beginning, or sometimes called just Bragg diffraction. But by firing X-rays at salt, we can look at diffraction. And this was ended up being very useful for looking at the shape of complex organic molecules. This picture to the left was used by people firing X-rays, focusing it down at organic material and seeing this weird X-type pattern with spots. And Rosalind Franklin looked at that shape and was able to work out the shape of DNA. That DNA is the double helix shape. It's because of this diffraction of X-rays. And this is just because of the existence of photons and the fact that light is also a wave. That's why this ties in. This whole idea that light has energy of HF, going with what Planck said, and then really Planck said HF is something, and then Einstein saying light is the HF, it led to us knowing the shape of DNA. Now, further proof that light can be a particle, that light has a light can be a photon with an energy of photon with energy HF, came by a man named Arthur Compton, also in the photo at the beginning of the chapter. Arthur Compton worked out something called the Compton Effect, which I'm going to do a quick aside here. Well, I did undergrad. When you're going to graduate undergrad and get your bachelor's, you have to take an oral exam where you get up in front of a group of 5 teachers and they can ask you anything that you've been taught at one point throughout the semester, and you need to be able to prove you remember it. And they literally told me, explain the Compton Effect, which I did very bad at. So still well enough I passed. It was my worst part though. So I hate the Compton Effect always, and it's going to make me angry every time I talk about it. But moving on. Dealing with the stuff we were talking about, X-rays, people saw that if we shot, instead of creating the X-rays, well, we shot the X-rays at the grid, like we were just saying, right? We're shooting the X-rays at the salt. Well, if they shot the X-rays at graphite, which has a nice crystalline lattice, what they saw is that if it came in with some wavelength lambda naught, the scattered waves had a different wavelength. That when the photons bounced off, when the X-rays bounced off the particles of graphene, aka off the protons that make up graphene, when they shot these photons at the protons, love that sentence, the wavelength changed. And that after bouncing off the graphene, they had a longer wavelength. Now, a longer wavelength means a shorter frequency. A shorter frequency means less energy. And what they found is that when photons bounced off something, their energy went down. And how much their energy went down depended on the angle of that it bounced out at. And this meant energy was lost with the collision. But what they found is when they shot the graphene is that it wasn't necessarily bouncing off the protons. It could bounce off the electrons. And that if you shot an electron with a photon, the electron would go one way and the photon would go the other. But we know conservation of momentum, right? That if I have something stationary, an object comes and hits it, and they both stop moving, well, if they both start moving, that means the other thing got energy. And that's what was happening. When you shined light at an electron, it would make the electron move. That the photon would hit the electron and make it move just like classical physics. When classical physics, if I take a if I take, I'm just gonna use my hands. If I take, I must have something I could use. Okay. Oh, random things. If I take this ball and fling it in here and they both start moving, they both have energy. That if this comes in, hits it, and they deflect out, they both conservation of momentum will hold true, but they both have energy. What we saw is when the photon hit the electron deflected. This is sometimes called Compton scattering instead of Compton effect. Because what happened is we scatter the electrons by hitting them with photons. And by shining light at an electron, you can make it move. You can shoot it flying off. And the reason the wavelength was decreased and the energy was decreased from the collision is because some of that energy went to the electron, which was now moving. Now, the change in wavelength before the collision and after the collision is known as the Compton shift. And it's actually findable that the Compton shift is going to always be Planck's constant divided by the mass of an electron in C times 1 minus the cosine of the angle. And this is further proof that light can be a particle, because if you hit an electron with a particle, the electron moves. If it was a wave, that wouldn't happen. And that's the logic. Any questions there?
No, I think I got it.
Right.
Unless someone else has a question.
Okay. Let's do an example problem. There's a photon of wavelength lambda naught, scatters off a free electron at point A. It produces a, when it does that, it basically forms a second photon, which I called lambda 1, which actually this called it lambda prime, so I probably should have called it the same thing. This photon then scatters off another free electron at B, producing a third photon, having a wavelength lambda 2. Really, I should have matched these things. And moving in a direction directly opposite the original photon, as shown in the figure. What is the Compton shift between 2 and 0? And so I'm just going to draw on this for now, where this was actually lambda 2, this was lambda 1. I should have used the same notation. Well, we know, well, that lasted me drawing those. We know the shift is lambda minus lambda naught h over MEC 1 minus cosine theta. And here I have two shifts. I have the shift 1, which would be lambda 1 minus lambda naught. And I have the shift 2, which is lambda 2 minus lambda naught, or lambda 2 minus lambda 1. I'm doing the Compton shift twice. The angle for the first one, well, there's the angle, theta 1. The angle for the second one is going to be some angle here, theta 2, which I haven't necessarily solved for yet. If I say the total shift, this shift plus the second shift, that's the total shift, because it'll be lambda 1 minus lambda naught plus lambda 2 minus lambda 1. My lambda 1s cancel out, and I get what I'm looking for. So what it means is I'm going to have to do shift 1, shift 2, and add it together to get what this problem asks for. So it would be as follows. Now, that right there, which I already had drawn, and now it's showing up again. This angle right here, that's also lambda 1, or angle theta 1. It's also theta 1 because the parallel axis theorem, that if we have two parallel lines, the inner angles are the same. So that means in this case, theta 1, oh, sorry, theta 2 is this angle. I actually marked the wrong angle for theta 2, and I'll explain why. The angle should be the angle between where it was going and where it went. That's why this is theta 1. Theta 2 is actually this big angle. It's 180 minus theta 1, because the angle between where it was going and where it ended up. So that means the cosine of theta 2 is equal to cosine of 180 minus theta 1. But anytime you have the cosine of 180 minus x, the cosine of 180 minus x is negative cosine of x. If you didn't know that fact, there's a trig function. So my equation on the left here becomes as follows. And with that equation, I can say the h over MEC is the same, so factor them in. It's 1 minus cosine theta 1 plus 1 plus cosine theta 1. That's just going to be, these terms are going to cancel out because I'm going to say plus cosine theta 1 minus cosine theta 1. So it's just going to be 2 times all of this, to which I can simply plug in and get an answer. If you want, you can put it in nanometers, but there's no need to. Questions? Okay.
No. Sorry, no.
There's a problem with this idea. It's not really a problem, but just let's think about this. So because light is a particle, it can deflect an electron. Cool. Got it. That works. But light is also a wave. And we can't just ignore the fact that light is also a wave. Light's a wave. It's a thing. Which I want to make a mulk to remember to fix the Compton thing here. And so let's think about this whole light being a particle and wave thing. Light can be a particle or wave. And the photoelectric effect and the Compton effect prove that it can be a photon. Interference and diffraction proves it can be a wave. And a man in 1924, also in that photo at the beginning, named Louis de Broglie, French, said that if photons have wave and particle characteristics, maybe electrons do too. Maybe electrons are waves. Why? Why not? And he said, you think about it. Photons have a certain amount of energy. The energy of a photon is hf, or hc over lambda. And we know, because of what Einstein said last chapter, is that photons have momentum. That the momentum of a photon is E over c. But E over c would be h over lambda. That means the wavelength of a photon is h over p. But if the wavelength of a photon is Planck's constant over the momentum, everything can have momentum. If I throw something across the room, it has momentum. Why can't other things have wavelengths? And what de Broglie said is that all particles with momentum can be viewed as if they are a wave. This was known as the de Broglie wavelength. And if they have a wave, if they have a wavelength, they got a frequency. All particles with momentum have wavelength and frequency. This was eventually proved in 1927. What this means is any moving particle can be treated as a wave. And wave mechanics works for everything. The idea that the light duality, that light is a particle and wave, people talk about that, but electrons do it too. Everything is a particle and a wave. Now, traditionally, this only will come into play for very small things. You could solve for the de Broglie wavelength of u as you run across a room, but it's useless. For an electron, this is important, that electrons will work like waves because they're very small and move quickly. And what people said is, you know what, if you treat electrons as a wave, then diffraction should work. And they set up a diffraction pattern small enough, shot electrons at it, and holy shit, it worked. And the whole idea of the photoelectric effect is if you shine light, you can get a circuit and move electrons, or X-rays that if you shoot electrons, you can get light, Makes a lot more sense when you know that electrons and light are the same thing. They're both particles and wave. So it makes sense it works backwards. It's the same. And that's the idea of the de Broglie wavelength. All matter can be treated as a wave. So, example problem. What's the de Broglie wavelength of an electron moving at 6 times 10 to the 6 meters per second, which is actually a reasonable speed, and a baseball that was pitched just for shits and giggles? If you want the de Broglie wavelength, it is Planck's constant over momentum. Planck's constant over mv. For an electron, mass of an electron is known, the velocity was given. The wavelength of that wave would just be plug in. And you get 1.21 times 10 to the negative 10 meters. That's 12.1 nanometers. That's in the ultraviolet range. That is a wavelength of light that we know how to deal with. And so it would make sense we have to treat the electron the same. If you do something like a baseball, though, and you plug in, you get a wavelength of 10 to the negative 34th. So small that you can't work with it. That's why we don't have to deal with this and can't see this unless we get microscopic.
So like would the isn't gamma technically like the smallest like range of wavelength? Would it be like
Gamma is highest energy, so
oh
yes.
highest? Okay, yeah.
No, it's highest energy, so it's shortest wavelength.
Okay, so it wouldn't be considered a gamma ray, would it? Or
No, it's
I
not a
don't think.
gamma ray because it's a different thing. Electrons
Oh,
have
okay, right,
mass.
okay.
And this is ultraviolet. This is a much larger wavelength than a gamma ray.
Okay. I
Gamma
guess I was
rays,
mixing up the two.
yeah. So keep in mind, I said this is on the form of ultraviolet. So this is more energy, sorry, this is less energy, but this is a longer wavelength than the X-rays we just talked about. This is at the very edge of visible.
Okay.
So let's do a complicated problem, and then I'll move on. Let's say a photon with a wavelength of 0.110 nanometers collides with a stationary electron. After collision, the electron moves forward because it just got hit, and the photon recoils backwards. Find the momentum and wavelength of the electron. I did not write this problem. So we're saying initially it's going to come in, the photon's going to come in with this wavelength. Well, Compton shift, we can find the wavelength it leaves at. Because Compton shift says if it whatever comes in, the angle comes out, that'll tell us our new wavelength. And so the change in wavelength will follow this equation, which means the new wavelength, lambda, would just be lambda naught plus h over MEC 1 minus cosine theta. Now, if this bounces completely recoils backwards, 180 degrees off, that means my angle is just 180 degrees. Where the cosine of 180 is negative 1. So 1 minus negative 1 is 2. And I can plug in some numbers. And so if this comes in at 0.110 nanometers, it's going to come back at 0.115 nanometers. Now, we can also say that this photon has momentum. The momentum of a photon is h over lambda. But conservation of energy says for any collision, the initial momentum equals the final momentum. And so I could treat this as a momentum problem, just like in physics 1. I'll say initially, my photon has momentum. Afterwards, I have a moving photon and a moving electron. So afterwards, my momentum is going to be the momentum of the photon plus the momentum of the electron. Now I have to say the momentum of the photon final is negative because it's moving to the left. And so conservation momentum will say that this momentum is my initial, because this guy's at rest. And final is this, where this guy is negative, this one is positive, because it's moving to the right. That means the momentum of the electron is as follows, which is very solvable. And that means if this photon hits an electron and bounces straight back, that's the momentum of the electron. That's how fast, that's its momentum entirely. If you wanted its wavelength, wavelength is h over p. There you go. If you want its velocity, you could do that too. You could just say mv and plug in the mass of an electron. It'll just be 1.18 e negative 23 divided by 9.11 e negative 31. It's moving at 1.29 times 10 to the 7th meters per second. Debatably, I might have been needed to use relativity for this. No, it's not quite to relativity. It would have to be up by one more factor. You want to do relativity when you're at about half c, and this is at like 0.5 c or 0.05 c. Does this make sense?
Yeah. Yeah, it makes sense.
Now, since I already talked about things I had to go through in undergrad, let's talk about things I had to go through in grad school. This has some very practical effects. The idea that electrons can be treated as a wave. There was a device called a scanning tunneling microscope. What a scanning tunneling microscope is a microscope that can look at things much, 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 much smaller than a traditional telescope. The reason why is with a telescope, we can look at, there's a certain amount of resolution based off wavelength. We covered that a bunch of chapters ago. We had an equation that worked out the minimum resolution for any wave due to the size of the wave and the size of the aperture. One of the limitations is the wavelength of visible light, but electrons have a much smaller wavelength. And so if we excite electrons, we can image objects by looking at the electrons bouncing off. And they're treating electrons as if they are light. And if you accelerate electrons super fast, they'll have a much lower wavelength than visible. And yeah, we can shine at something, bounce off, and see what it looks like. This is a picture of some weird dust mite thing that someone took with an STM microscope. Their resolution get tiny. This right here says I can have a resolution of 5 nanometers. That is taken from the textbook I used to use. But I'm going to be honest. My research used to be on very, 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 very small things. When I was at SUNY Buffalo, we had a STM microscope scanning. This is a transmission microscope as opposed to a scanning tunneling. Works a little differently how it works. I'm not going to get the details, but it's the same idea. We're taking electrons, shooting it, looking at the electrons. You could excite electrons with 200,000 volts, giving an electron velocity of about 0.65 c, relativistic speeds. And this could give a resolution of 0.1 nanometer. This picture right here is from my thesis defense. And I was looking at hunks of indium gallium arsenide. That was, if you look at that scale, 1, 2, 3, 4, 6, 4, 3, 2, 1, 8, there are about 1.8 nanometers across those things that are circled. And you can do that because you're looking at things on such a tiny scale because we're not using light, we're using the fact that electrons are waves instead. Now to go very nuts with this, and I'm only gonna do this for one slide. This is, okay. Sticking to my thesis defense, this picture involved layers of semiconductor materials, gallium arsenide, indium gallium arsenide. I did a thing with this whole basis was a thing with tunneling. The next few pictures are also for my thesis. Okay. If I take a ball, throw it at the wall, it bounces off. If I take a ball and want it to go over the wall, I have to throw it over the wall. I cannot take a ball and throw it through a wall. Well, I guess theoretically I can if I go like Superman level, but right, you throw something at a wall, it bounces off. But let's talk about what happens when light hits a material. We said anytime you shine light on a thing, some will reflect, some will refract. That because light is a wave, that if you shine light at a material, some will pass through, some will bounce off. Some will be absorbed. We ignored absorption, but it also some will be absorbed. But now we're saying electrons are a wave. And so logically, if you fire an electron at something, some should reflect and some should refract because electrons are a wave. And this is true. This is called quantum tunneling. If you shoot an electron at a wall, some will bounce off, but some will go right through it and say, fuck it, I don't care, I'm going through. Because it's a wave.
So like it can do this through like any material?
Yeah. Yep. So my research, among other things, was on gallium arsenide quantum wells. This picture on the bottom left is from my thesis. And we have this is showing the potential at various spots, basically showing the wall. And I would have electrons be injected through aluminum gallium arsenic barrier. They'll just pass right through quantum tunneling. This is heavily used in semiconductor physics. If you're doing anything with semiconductors like microchips and things like that, I was working on spintronics, the beginning of quantum computing. It's heavily used that you can just shoot them right through any wall because they're tunnel. Because it's a wave. It's not a particle. It's a wave. Now, to go even more nuts on this, because the kits keep coming. Next chapter, we are going to talk about atomic physics. Next chapter, we're going to talk about the atom and the models of the atom. I'm going to jump ahead to the conclusion of that chapter real fast because it all ties into this. Around the time this was all being discovered, once again, all of these people are in that same photo together. So same group of people. One of the people in that photo was a name named Erwin Schrödinger. And Schrödinger said, okay, electrons are waves. Got it. If electrons are waves, and if electrons move through space-time, following Einstein's idea, got that too. So we got de Broglie, we got Einstein. If both of those are true, let's treat all matter as a wave. And let's say that all matter has a, what he called a wave function. And the reason he was doing this was trying to prove the model of the atom, which we're going to talk about this next chapter. This was in response to a man named Niels Bohr and his model of the atom. And what he said is that if something is a wave, we can define its wave function. And what its wave function does is we can use it to define the position of something as a function of time. See, if we look at an electron, and we just look at an electron, it's so tiny we can't really look at it. And the only way to look at an electron is like to fire light on it, but if we fire light on something, Compton scattering, it's in a different spot. We can't look at an electron. I'll go into this more detail in a few more slides. We can't look at an electron without messing it up. So instead, we can mathematically predict where it would be. And he made an equation to describe the location of an electron in the hydrogen atom. Now, for the record, it has only been solved for the hydrogen and hydrogen-like atoms. The reason why is a hydrogen atom is one proton, one electron. And if you have one proton, one electron, we got a proton, we have an electron orbiting. There's a Coulomb force between them. If you add more electrons, here's my second electron. What's going to happen is there'll be a Coulomb force between this electron and the proton, and between this electron and the other electron. And as the electrons move relative to each other, that's going to be constantly changing what the Coulomb force's direction is, and becomes nearly impossible. But if you have only one electron and any number of protons, but only one electron, this wave function can be used to describe exactly where an electron is and what it's doing. Now, he represented the wave function with this symbol capital psi, and says that if you find psi using Schrödinger's equation, Psi squared is the probability of the location of a particle at any given moment. And what he said is, you never know where anything is. And we're going to come back to that in a second. That you never know where an electron is for sure. It's impossible to know. But we can figure out where it's most probable to be. And if you find the wave function, square it, that's the probability. And he said, this is the equation. IH bar, the partial integral with psi with respect to t, h times psi, if you're dealing with time. If you're not dealing with time, just h psi equals e psi. Now, what this equation means. I want to once again say, this has never been solved for anything more complicated than hydrogen, because this equation is so goddamn complicated. The h in this equation is called the Hamiltonian operator. And it's a fancy way of saying kinetic energy plus potential energy. This time-independent Schrödinger equation literally says total energy equals total energy. H is simply kinetic energy plus potential energy. And so the equation really is the kinetic energy of the particle plus the potential energy of the particle equals the total energy of the particle. But H has a mathematical formula, like I just wrote right there. Well, H bar is H over 2 pi. And that upside down triangle squared is called the Laplacian. And so really this equation should be this. And this is still a simplified version. It's fucking nuts. And see, some of the logic here, I'm not going to play that video today, is because he was saying you can't know where a particle is. That you can't know where a particle is, you can only say where it will most likely be. And see, the basis of that ties into something called the uncertainty principle. The uncertainty principle was actually written by someone else. Schrödinger did this stuff, what I say, in 1926. The uncertainty principle was in 1927 by a man named Werner Heisenberg. In Breaking Bad, he goes by the name Heisenberg. This is the Heisenberg he named himself after. Also in that picture at the beginning of the chapter. This one, not the Breaking Bad one. What he said is anytime you make a measurement, there is always uncertainties in the measurement, right? That if you measure the length of something with a ruler, you can only get your length as exact as your ruler. Classical mechanics says the uncertainty in any measurement is as big as it needs to be, how good your ruler is. But what Heisenberg said is if we are doing stuff with quantum, there has to be a limit to how accurate we can get. Because let's say we are going to look at, well, let me not get ahead of myself. And he said the limit was as follows. That if you measure the position of a particle and you have an uncertainty in position of sigma x, and you measure the momentum of the particle, and the uncertainty and the momentum of the particle has an uncertainty, sigma p. The uncertainty of position times the uncertainty of momentum must always be greater than or equal to h over 4 pi. You can never know the exact location and momentum of an object. If you know its location, you don't know its momentum. If you don't know its location, if you know its momentum, you don't know its location. And there's actually two versions of this equation. One for momentum and position, and one for energy and time. We're going to normally do the position and momentum one. See, the reason for this is because the process of making a measurement changed the measurement. Let's say you want to look at the position and momentum of an electron. And you say, okay, I'm going to look at the position and momentum of an electron. I want to look at that electron. I need to shine light at it. Because the only way to look at something, how our eyes work, is by shining light at it. And so if you look at an electron in a high-power microscope, you shoot light at it. If you shoot light at an electron, that's Compton scattering. The second you hit an electron with light, you've deflected it. And so if you look at an electron and you know where that electron is, you have changed its momentum because of Compton scattering. That the process of knowing something's location will change its momentum. If you make sigma x small, sigma p becomes big. Likewise, if you can figure out how fast something is moving, to figure out how fast something's moving, aka the momentum or tied to momentum, you normally have to get two species and say goes from here to here. Figure out how long it took to travel that distance, multiply by mass, that's momentum. But if you're bringing it through two gates, you're not saying where it is, you're saying it passed through an area. And so the process of knowing what momentum is, you got no idea what position is. And so it's a limit of how certain you can be. This stems from the idea that if you make a measurement, you change the measurement. That anytime you make a measurement, you officially change it. And that making, and what he went further with, is the process of making an observation changes what the observation is going to be. That anytime you look at a thing, you cause it to be a certain way. And the process of observing something is how something is forced into being. His friend Schrödinger took this and ran with it. And this was the beginning of the Schrödinger's cat experiment, which isn't really an experiment. No one ever did it, but is a thought process. And I'm sure you've heard it before, but here's the idea. Let's say you take a cat and you put the cat in a sealed box with a vial of poisonous gas. The vial is attached to a device that has a 50% chance of letting the gas out and killing the cat. And the box is not see-through. We're not worrying about the cat suffocating because there's no air holes. We're not worrying about the cat starving to death because there's no food. It's not going to be in there that long. You put the cat in the box, you put the vial. There's a 50-50 chance the cat dies. What Schrödinger said, based off Heisenberg's stuff, is that if there's no way to tell if the cat is alive or dead, let's make that assumption, right? That until we open the box, we have no idea. When the box is closed, 50-50 chance. Well, what Schrödinger said is until you open the box, the cat is both. That the cat's wave function allows either, because it's all probability. And that it's not that the cat is either alive or dead. While the box is closed, the cat is both. The cat is alive and dead. This is also the basis of multiverse theory, so that's fun. Because it's just as equally probable. And if it's just as equally probable, they both are true. And it says if you open the box, when you open the box and check, that is what kills the cat, or that is what saves the cat. That the process of looking at the cat collapses the wave function and makes reality happen. That until you look, it's both. Once you look, then we have one or the other. Okay? Now, normally I play a video here, but I'm almost out of time and I want to do an example problem instead. But there's the link. Are we good so far?
Yep.
Depending on how long the example problem goes, maybe I'll still play the video. It's only a minute long. So, example problem first. Say you know the position of an object, and you have uncertainty in the position of 1.5 times 10 to the negative 11 meters. What is the minimum uncertainty of the speed of the object for an electron and ping pong ball? Well, the uncertainty position times the uncertainty momentum is less than or equal to h over 4 pi, where p is mv. If there's no uncertainty in mass, sigma p is going to be m sigma v. Now, if I want the minimum uncertainty, that's going to be when it's equal. And so I can say the uncertainty in momentum, I'll just divide both sides by the uncertainty in position. But the uncertainty in momentum, I said, was m sigma v. So I can also divide both sides by mass. For an electron, if you have that tiny ass uncertainty in position, your uncertainty in velocity is 3.86 times 10 to the 6 meters per second. That's not what the velocity is. That's the wiggle room. That's a huge uncertainty. Basically, if you know what an electron is, you got no fucking idea how fast it's going. Now, for a ping pong ball, which has a much larger mass, it's a tiny ass number. And that's why we don't normally deal with this. It only comes into play for very, very small objects. Okay? Okay. It is officially, I got 1 minute. This video is too long. And just hit 150. So I'm not going to play the video. I do recommend watching it. The link is there. It is it gets into multiverse theory because Schrödinger's cat gets into multiverse theory. The link was right here. Other than that, we'll do example problems on Friday. And you have homework due tonight, and that's where we're at. So have a good day.